Shall I start?
Yes, sir. Yes, sir.
Okay, so right now I will discuss about the 8086 microprocessor, which is 16-bit microprocessor invented by Intel Corporation in 1978. So it's first 16-bit microprocessor. The 16-bit microprocessor means it can access 16-bit data at a time. So the frequency of this microprocessor range is from 5 to 8 megahertz. The operating frequency 5 to 8 megahertz. So these frequencies that depends on the version of every 8086 microprocessor. So here are some features like this can be used to execute the instructions at 2.5 million instructions per second, and the execution time of one instruction is 400 nanosecond. The memory portion, which is very important in this case, 8086 has huge memory space, that is 1 MB. Now why 1 MB memory space is there? Because it has 20 address lines, 20-bit addresses there. So according to the calculation of total memory space, all of you know about the calculation, like 2 to the power number of address lines is equivalent to the total memory space. Here in this case, in 8086, the address lines are 20, so 2 to the power 20, which is equivalent to 1 MB memory space. Another feature in 8086 is it has 6-byte instruction queue, so that it can store the instructions early and it can be executed one by one. Okay, so here the instructions fetched from memory and are placed in it before they are executed. Why this 6-byte instruction queue has been implemented? Because of the pipelining architecture. The new technology which is implemented here in 8086 microprocessor, that is a pipelining architecture. Now, what do you mean by pipelining? Pipelining means at one time, two simultaneous operations can be performed. Like, as for example, in previous microprocessor, like in 8085, how the instructions will be executed one by one sequentially. The first instruction must be fetched from the memory, then decode, then it is ready for execution. Okay, and the second instruction will be started from fetching it from the memory, then decode it, then the execution. The third instruction will be in this way. The corresponding instructions are executed in sequential manner. So first fetch, decode, then execute. But in 8086, if first instruction is being fetched by the processor from the memory, then it stores inside the queue, and after storing it, now it is ready to decode and execution. Decode and execute. When the first instruction is being executed by the microprocessor, the second instruction must be fetched from the memory and it stores inside the queue. And when it is ready for execution, the third instruction is side by side, it is fetched. So one instruction is being fetched at the same time, side by side. The second instruction is fetched from the memory and it stores inside that queue. So two simultaneous operations are performed at the same time. One is the execution, another is the fetching. So execution, then the fetch, then execution. So fetching is continuous form and execution is going on. Okay, that is called the pipelining. So because of this pipelining, the instructions executions are in very fastest way. So that's why it has higher execution speed and it has larger memory size. The power supply requirement to operate this microprocessor is again 5-volt power supply is needed, and it is. So here is your block diagram of functional block diagram of 8086. I will discuss every block of this diagram. First of all of you have been noticed that this structure it is divided into two parts. The upper portion, which is called the BIU, bus interface unit. BIU stands for bus interface unit. EU, that is execution unit. Okay, so upper portion, that is called the BIU unit, and lower portion, which is called the execution unit. The architecture, it is divided or separated by this dotted line. Okay, now the upper portion BIU has many functions, like it is connected to the outside of this processor, it is connected to the external side. External means the memories are external to the processor, the IO devices, both are, all these are connected via this BIU section. EU has no external circuitry connection, it is only for decoding purpose and the execution purpose. So if here BIU first fetch the instructions from the memory, and this data bus is used to transfer that instruction or data, whatever, and stores inside this queue. And after storing it one by one, the several instructions are stored. So maximum 6 byte can be stored in this queue. And when it is full, then one by one it is going for execution purpose. So it goes to the controls unit, control system, control unit for decoding purpose, and then from this position it goes for execution purpose. Okay, so in this BIU circuit, in this BIU section or EU section, in this architecture, there are two arithmetic blocks, this one and the ALU. Okay, so it has some significance of this type of structure. Why? Because in any arithmetic circuit, you need two inputs and one output will be generated. So two input must be given in this way and one output will be generated in this way. Here for ALU also, it needs two inputs in this way and it is used to generate one output. Okay, all other blocks are represented in a rectangular form. Now, before going to discuss of this individual block, you need to know the memory organization. It will help you to understand this architecture or functional block diagram in details. So this is the memory. Here, the total 1 MB memory space is given, 1 MB memory space. Now this 1 MB memory space, it is divided into, like this one, it is divided into 4 segments, and the segments are called extra segment, which is ES, code segment, which is CS, stack segment, which is SS, and data segment, which is DS. 4 segments are there. Each segment is 64 kilobytes long. 64 kilobytes. The size of each section is 64 kilobyte. Now each 64 kilobyte, it is used for specific functions. Like for every segment, it has specific functions. For example, code segment, that is used to store the instructions. So programming code must be stored inside this segment. Data segment, it is used to store the data. Stack segment, it is used to operate the stack portion. Stack, the structural data can be stored in this position. The extra segment, which is also used to store the data. So it is the extended version, this extra segment, it is the extended version of this data segment. So individually, this segment, each segment has a specific function. Now, why these sections or segments are divided? Why these 4 logical segments are divided in this way? So total 1 MB memory space, it's a huge memory space. Okay, now this huge memory space can be divided into 4 segments, such that according to your requirement, which segment is to be used, it depends on your instructions execution. Like the reason is, like, as for example, suppose you have one book, it has 10 chapters. Each chapter contains 10 pages. Okay, now if you'd like to find out the page number 64, so how can you go page number 64? Either you can search it from the initial position 1, 2, 3, 4 and all the way up to 64. Otherwise it can be given in this way: chapter number 6 and page number 4. So here chapter number 6, so chapter number which is equivalent to this segment, and the page number is 4, which is equivalent to the offset address. These are called segment address. These are used to store the segment address. So that's why these 4 segments are there. And another is the offset address. So the combinations of segment address and the offset address, you can easily find out the actual physical address of data byte, where the data byte is situated or it is stored. Okay, like you have used in your PC, or desktop or laptop, you can give a name of that any location as folder name and file name. Okay, so you need to go to search any document in such file. First you need to go to the folder name, then to the file name. In this way, if microprocessor needs to find out any data in any memory address which is the real address, so it needs 2 locations. One is the segment address, another is the offset address. So for each segment here it is equivalent to the folder, and inside this segment there are lots of offset addresses which is equivalent to file name. Okay, so for each segment individually offset registers has been assigned. For every segment the offset registers are different. Like in this example here, so the total memory space is 1 MB and the address lines are 20 bits wide, 20 bits. So here it is started from 00000, and the last address of memory will be FFFFF. Now according to the 20-bit address, each hexadecimal digit is equivalent to 4 binary digits. Okay, so that's why it is started from 00000 to FFFFF. Clear? Now this total memory, it is divided into 4 segments. Like this one, it is used for data segment. Like this position, it is used for code segment. It is used for stack segment. Then it is used for code segment, and this is used for extra segment. The remaining memory addresses are empty, and those can be used for future purpose. So that's why there is enough memory if these are divided into 4 logical segments. So assume my data segment has been started from this memory location 3000. Now inside this data segment 64 kilobyte locations or 65,536 locations are present. Each location is called the offset address. So offset address for data segment will be started from 0000 to FFFF. Again, for stack segment, it has the stack memory location, starting memory location, segment memory location, which is the base address. Here in this case 5,000, and inside this stack segment there are 65,536 locations, and it is started from 0000 to FFFF. So your segment will be fixed, but your offset will be changed. Okay, so in this way, for code segment there is a base address or the starting address, and inside this segment there are several locations. For extra segment, that is also, it has base address of the starting address of this segment, and inside this there are 64 kilobyte locations are available. Okay, so now to calculate the actual data address, where the data is being situated, you need to calculate, you need to combine both the segment address as well as the offset address. Okay, how can you calculate the physical address? Here, suppose my code segment is given as 7480. Code segment address is given as 7480, and my offset address is given as 2400. Then using the formula, which is code segment into 10 plus offset, is equivalent to the actual address, which is called the physical address. So code segment into 10 means 7480 was my base address. Using the multiplication of 10 in hexadecimal number system, it will be 74800, and offset will be added to this segment address. Now the combinations of this segment address and offset address, the real physical address will be generated, and that is the actual address. Okay, so in this way the 20-bit physical address will be generated. So one thing you have to notice here, that is every memory location, whether it is a segment address or the offset address, only 16-bit memory address will be given, and 20-bit physical address will be generated internally. Okay, so you need to initialize the memory addresses in 16-bit form, and the actual address will be generated in this way, which is 20 bits in size. Here, so the function, this addition will be, so this addition will be carried out in this block, this adder block. Okay, so here these are the registers like ES, CS, SS, DS. These are called segment registers. These are called segment registers, and the use of these registers is to store the segment addresses. Like ES, it is a 16-bit register. CS, it is another 16-bit register. SS, it is another 16-bit register. DS is another 16-bit register. So why these registers are 16 bits? Because these registers are used to store the memory addresses. Which memory addresses? Segment addresses. So segment addresses are 16-bit wide. That's why it is these registers are 16-bit in size. So for every segment, the offset is fixed. Like if code segment is used, the segment address will be stored in code segment register, and the required offset address will be stored inside instruction pointer IP. That is the offset register, which is again 16-bit in size, because it is also used to store some address, and we know that generally the memory addresses are, all memory addresses are 16-bit in size. So the combinations of this code segment and IP instruction pointer, this is the segment address, this is the offset address. Combinations of these two addresses will be generated. It is used to generate the physical address, which is 20-bit in size. Now one address is given in this way, another address like segment address is given in this way, offset address is given in this way. The combinations of these two addresses are operate here in this position, this addition, and the formula is the segment address into 10 plus offset address. Okay, that is the 20-bit physical address. When the 20-bit physical address is generated, this address must be given to the memory device. Now, using that real address, 20-bit physical address, the required number of instructions or data will be fetched using this data bus, and it stores inside this queue. Now, from this queue, one by one, the instructions are decoded and then executed. Okay. So why this 6-byte queue has been implemented, or what is the function of this 6-byte instruction queue? 6-byte means you can store, this queue has been implemented to store 6 byte at a time. 6 byte. It doesn't mean that 6-byte instruction means this queue is used to store the 6-byte instruction. Because here in 8086 the maximum instruction length is 6 byte. So that's why to store one complete instruction after being fetched by the microprocessor from the memory, it is to be stored inside this queue. So some instructions may be 1 byte, maybe 2 byte, 3 byte, and all the way up to 6 byte. So whatever be the size of that instruction, so no problem, that will be stored inside this queue. And when this queue is full, no instruction can be fetched by the BIU circuit until upper 2 byte is empty. Until upper 2 byte is empty. Now why you need to empty this upper 2 bytes until no instruction can be fetched? Because we know that 8086 is a 16-bit microprocessor. It's a 16-bit microprocessor, so that means it can access 16-bit data at a time, or in one clock cycle. So if the upper position only 1 byte is vacant, why you need to waste the cycle? Why you need to waste the cycle? That's why if 2 bytes are vacant or empty, these positions are empty, at one machine cycle, microprocessor can fetch the data or instruction at one cycle, so that at one cycle these upper 2 bytes will be full. So that's why no instruction can be fetched until this upper 2 byte of this queue is empty. Okay, so that is the function of 6 byte instruction queue. So when the first instruction is being fetched by the processor and stored inside this queue, and it goes into the circuit for decoding purpose, then execution purpose, the second instruction will be fetched side by side. So one instruction is executed in this position. At that time, the second instruction is being fetched and stored, and in this way the next instruction will be fetched and stored inside this queue until this queue has been full. Okay, so here these are the registers for special purpose to store the segment addresses. That's why these are called segment registers. One offset register is included in this position, that is the IP, because first you need to access the instruction for any operation using microprocessor. What will be the execution of instruction. And now we know that every instruction has two parts. First is the opcode, second is the operand. Now to fetch any kind of instruction means to fetch the opcode first, then the operand part. Okay, now to store this opcode, you need this code segment, and if code segment has been selected, that is fixed by the Intel, you need to operate the offset address or offset register as IP, instruction pointer. So these are fixed. If CS has been considered, then you need to consider IP. But IP cannot be combined with any other segment addresses. Like if you have used the ES, extra segment, IP cannot be used. If you can select the DS, data segment, IP cannot be used. For this purpose, like ES, SS and DS, different registers are available. Those can be used as offset registers. And these are SP, stack pointer, base pointer, BP, SI, source index and destination index. These registers are special purpose registers. Those are stored inside this block, which is called in this section, which is in execution unit section. Is it clear up to this much, everyone?
Sir.
Yes, sir.
Sir, I'm telling that in between the two set address means the code set and the extra segment and the code segment. Why there is a small gap?
Small gap? Can't understand.
Small gap means that it is starting from the 2000 to 2FF, then again from 4F,
you can initialize any segment in any position within 1 MB. Okay, it is not mandatory that always you need to store these segments individually in 2000 or 3000. Within 1 MB, you need to create, or microprocessor according to the structure, it is created within 1 MB anywhere these 4 logical segments. Okay.
And also, sir, there is a memory space gap between the two segments. Why it is
maybe because 1 MB memory space is there, you can select any position to initialize any segment. Like code segment has been initialized in 2000. Okay, from 2000 it goes up to 2FFF. Then you can select the extra segment in 4000. Okay, then stack segment can be initialized in 5000, or data segment can be initialized in 9000. So in between there must be gap. No problem, because every operation will be performed according to your selection. Because within that code segment, which is initialized from 2000 to 2FFF, every instruction will be written in this position. Okay, no instruction will be written in 3000 or 4000. Okay, like if you want to store any data, so if data segment has been initialized into 9000 memory location, so always you need to use the 9000 memory location for data storage purpose. You can't use 5000 or 6000 these memory locations. Okay, because for storing the instruction, some segment has been specified. For storing the data, another segment has been initialized. For storing the stack, for operate the stack, or to store the structural data, you have stack memory location, okay, which is initialized in another segment. Okay, so individually these segments can be initialized anywhere within 1 MB memory space. Okay.
Yes, sir.
Okay, so I
Sir,
will go
please
to the
can you
next section.
explain once more the
স্যার বলছি কি সবাইকে আনমিউট করবেন না, রাজশ্রী একটা কোয়েশ্চেন আছে ও message করছে।
No, question answer session will be forwarded to the next last 10 minutes. Okay, right now I need to deliver this lecture. Okay, so what is your confusion and everything else regarding this topic?
স্যার 6 বাইট ইনস্ট্রাকশনটা বলছিলেন না, একটা ইনস্ট্রাকশন কিভাবে আসে এন্টার করে, ওটা একটু বলবেন। ওই 6 বাইট প্রিফেজ কিউএ।
Here the first is if the instruction is 6 byte long, 6 byte. Okay, so total 6 byte at a time will be executed and transferred or fetched by the processor, and it goes in this way using this data bus and stores inside this queue, because queue has maximum can store 6 byte at a time. Okay, so 6 byte. So if 6 byte instruction is being fetched by the processor, that 6 byte instruction will be stored in this way. Like in case of 8085 microprocessor, there is a 3 byte instruction. Okay, so you need 3 memory location to store it. So one by one it will be fetched. Now if 6 byte instruction in case of 8086, so 6 memory locations will be required. So within that 6 memory location, each memory location can contains only 1 byte at a time. 1 byte means 8 bit. So it's here the queue is 6 byte, means 8 bit. 8 bit, one space it is used to store 8 bit at a time. So here 8 bit will be stored, another 8 bit, another 8 bit, another 8 bit, another 8 bit, and the last 8 bit. The combinations of these all 6 8 bit, it's called a 6 byte instruction. Clear? Clear? So I will discuss the next section, which is the execution unit section. Okay, so the lower portion is called the execution unit, where certain registers has been implemented, like these are these AH, AL, BH, BL, CH, CL, DH, DL. These are general purpose registers. Individually AH is 8 bit, AL is 8 bit, BH is 8 bit, BL is 8 bit, CH is 8 bit, CL is 8 bit, DH is 8 bit, DL is 8 bit. Now the combinations of these two 8 bit register, one 16 bit register can be formed, which is called AX. So the first register, which is called the AX, means accumulator, which is 16 bit in size, but individually you can operate it to operate any 8 bit data. Like you can use AH for 8 bit purpose, or you can use AL for another 8 bit purpose, and the combinations of these two 8 bit can create so one register, which is AX, called as accumulator. Next is the BH and BL, and combinations of this BH and BL, it creates BX register, BX register, which is 16 bit register. Here, so AHAL, it creates accumulator. Okay, and BHBL creates the BX register, or it is called the base register. Now next is the CH and CL, which creates the CX register or count register, and DH and DL, the combinations of these two 8 bit register creates a 116 bit register, which is used as data register. So to operate any 16 bit of data, you can use AX or BX or CX or DX, or according to your requirement, if you need to process any 8 bit of data, you can use either the upper 8 bit or the lower 8 bit of that register. If you can use the upper 8 bit, so AH can be implemented. If you need to use the lower 8 bit, AL can be implemented. Okay, in this way, all the registers like AX, BX, CX, and DX, all these registers can be used as your 16 bit register, or individually these can be used as your 8 bit register. And these are general purpose registers, and these registers are used everywhere, like to write any instruction. These registers are used. That's why these are general purpose registers. Next register is here. The special purpose registers are SP, stack pointer, base pointer, SI, source index, and DI, destination index. All these are 16-bit registers. These are why so special, because these are used to store the offset addresses. Like if stack segment is used for stack operation, you need to use the SS register to store the stack address or the segment address. Now if stack segment is used, then you need to use the offset also. In that case, either you can use the stack pointer as your offset register or base pointer as per your addressing mode. You can use any one of them, SP and BP. Stack pointer and base pointer at the offset register is stack segment is used as your segment register. SI and DI can be used as your offset register if DS and ES, data segment and extra segment, can be used. So you can't combine this CS with this SP, or you can't combine this CS with BP, or you can't combine this CS with SI or DI. Okay, Intel has been fixed these combinations. If you can use the CS, you need to use the IP as your offset register. If you can use as your segment register as ES, you need to use SI or DI. If DS segment is used, you need to use either SI or DI. If SS segment is used, stack segment, then either you can use the SP, stack pointer, or base pointer. So these are your special registers. Okay, only 8 registers are available. 8 8-bit registers are available as your general purpose registers. The combinations of 2 8-bit register can create one 16-bit register, which is again 16-bit general purpose register. Okay, next is here the arithmetic logic unit. So every operations are performed, arithmetic and logical operations are performed in this block, in this section. Like if you want to add two numbers, suppose one number is stored in BL like 5, another number is stored in CL like 4. So you need to add 5 plus 4 and the result will be 9, which will be stored inside BL. So what will be the program? Like you can write it and move BL comma 05, move CL comma 04, then add BL comma CL. So add BL comma CL, the meaning of this instruction is addition between the content of BL and the content of CL, and the result will be stored inside BL. Okay, so one difference between the 8085 and 8086 is 8085 all the operations are accumulator oriented operation. By default, accumulator will be operated 1 data byte, which will be stored, and the result will be stored automatically inside the accumulator. But in this case, in 8086, you can add any register to any register, and the result will be stored according to your requirement. Any register can be used to store the result. So if it is written as add BL comma CL, means the after addition the result will be stored inside BL. Okay, so according to the first instruction, suppose it is written as move BL comma 05. So move BL comma 05 will be stored or must be fetched in this way and stored inside this queue. Okay, then it goes to the control unit section for decoding purpose of the opcode. Like move BL, it has specific opcode which will be decoded by this control unit. Then it gives the information and it stores the value to the BL. The second instruction will be move CL comma 04. So 04 will be moved into CL. In this way, the second instruction must be fetched and stored inside this queue. After that, it goes for decoding purpose and execution purpose. So 4 will be stored inside this CL. Next instruction is to add them. Add BL comma CL. So when this add BL comma CL instruction is being fetched and stored inside this queue, after that it goes for decoding purpose. So here the opcode has been interpreted and it gives the signal to every according to your requirement. According to this addition requirement, it gives the signal to the BL and CL that you need to add. Again, it gives the signal to the ALU, you need to perform the addition. Okay, so it gives the signal to this register BL to release its value. So that value will be transferred through this bus and it is stored in this position 05. Then it gives the signal to the CL to release the 04 data byte, and this will be given